So welcome back. We stay with lecture 7.1. So it is 7.1. So this is lecture 7.1b. The second part of our lecture. We were talking about grinding temperature and that belongs to module number 7. So first, now you need to understand the heat transfer that takes place in grinding. So here is the total heat generation that is expressed as QT dot. It is rate of heat generation in grinding, and for all practical purpose we will write it as Ft into Vs. Now this is the basic dimensioning that should always be there when you are drawing a schematic. Now this heat get apportioned into different places. What are those places? One place is chips are produced. So some amount of heat goes into the chip. How much it is? We will talk about it later. So some amount of heat goes into the chip. Where else does it go? Some amount of heat also enters the workpiece. This raises the workpiece temperature. These are heat rates. What else? There is a wheel. So some amount of heat enters the wheel as well. So this is the third component of heat rate or power, grinding power, where it enters. And there is a fourth component. What is that fourth component? Already we have mentioned in the previous lecture that in grinding you would be applying grinding fluid or coolant or lubricant, whatever you call it. So this is your grinding fluid application. So a grinding fluid would be applied to provide cooling and lubrication action. So some amount of heat would also enter it. Exactly how much, that we do not know at this stage. So what we know is this. So this is the chip, this is the workpiece, this is the grinding fluid, and this is the grit. Now what are the mechanism by which these heat transfer takes place? This particular heat transfer primarily takes place by convection. It is a case of forced convection because grinding fluid is typically applied at not very high velocity, but they are applied with some amount of velocity. So it is a case of forced convection. What is this? This is conduction, and along with that chip stream, they go away from the grinding zone, and along with that, as the temperature of the chip stream increases, they take away some amount of heat. Some amount of heat also enters the workpiece, and this also takes place by conduction. Some amount of heat enters the wheel, and that also takes place by conduction. So these are the different heat transfer mechanism which occurs in grinding. Now let us go into something which is called apportionment coefficient. Before apportionment coefficient, I need to introduce something else. There is something which is called heat flask. This is called total heat flux. And how much is this? This is nothing but capital QT divided by LC into BW. What is this LC into BW? This is the contact area in case of flange surface grinding. In other kind of grinding, whatever would be the expression of contact area, that will come out. Similarly, there are something else which is QW. QW, we need not use the dot. We can get rid of dot. There is no need to use the dot. It is simply QW QT. So QW is basically heat flux entering the workpiece, and this is equal to capital QW dot divided by LC into BW. What is the unit of this one? Please try to recall. This is FT into VS. So this is in watt. So this heat flask is nothing but watt per meter square or watt per millimeter square, in whichever unit you would like to express that. There are several more such heat fluxes. One is QCH, one is QFL, another one is QS, and they are simply expressed as this. Does not provide a view into apportionment coefficient. So we will go towards apportionment coefficient, and for that let us use a different color. Maybe this one will be more suitable. No, I will use a different. I will use this color so that it is distinctly different. Now apportionment coefficient, say let us write an apportionment coefficient RW. This is expressed as QW by QT. What is the physical meaning of that? Fraction of total heat flux that is entering the workpiece. Similarly, you have RCH, which is QCH by QT. You have RFL, which is QFL by QT. You have RS, which is QS by QT. What is QS? QS is the amount of heat flask entering the grinding wheel. Now it is interesting to note that QS plus QCH plus QW plus QFL equal to QT. Why is it so? Because the total heat generation rate is equal to the sum of these four. And if I divide the right hand side and left hand side by LC into BW, if I divide that, the right hand side and left hand side, then I will get this particular expression. Further, you have understood that if you divide this equation by QT on both sides, what would you get? On the right hand side, you will get 1. On the left hand side, the first one would be QS by QT, which is nothing but RS. Next one is QCH by QT, which is nothing but RCH. Next one would be RW plus RFL. So there are few interesting equations that we have derived. One is this one is this one, other one is this one, and the most important one is this particular one, estimation of total heat flask. Here this would be equal to FT into VS divided by LC into BW, because QT dot is nothing but FT into VS. Now let us see what is coming. This is heat transfer in dry grinding. So there are different possibilities of dry grinding. This is A, this is VW, this is NS, and here you have heat generation, and the amount of heat generation is FT into VS, which is expressed as QT dot. So let me rewrite it properly. So this is QT dot. Now in dry grinding can be undertaken by conventional wheel, it can be undertaken by super abrasive wheel. And there is a major difference between the thermal characteristics of this one. Vitrified conventional wheels, their effective thermal conductivity is very poor, whereas metal bonded or monolayer super abrasive wheels, their thermal conductivity is very high. And how does it affect heat transfer? That we will try to write down. So what we can write down from the previous slide, QW equal to QS plus QW plus QS plus QCH plus QFL equal to QT. Now this is dry grinding. As because this is dry grinding, there is no application of grinding fluid. If there is no application of grinding fluid, QFL would be 0. Why? Because there is no grinding fluid, there would not be any heat there would not be any convective heat transfer from the grinding zone to the grinding fluid. So this will become 0. Another interesting thing will happen, somehow for certain situation this QS will become 0. When it will become 0, what is the physical meaning of QS becoming 0? That is no heat or negligible amount of heat is entering the grinding wheel. Now the question is how far this assumption is true. So what we are when we are assuming this is we are assuming when you are using a vitrified wheel, say Al2O3 or silicon carbide. These are ceramic materials and their thermal conductivity is very less. Now there is another very important and interesting thing. I say for example a grit is passing from this particular point to this particular point with a velocity Vs, and thus time taken by a grit to go from this point to this point is LC divided by Vs, and this we have estimated earlier. Once again we will estimate today. Let us say LC is 3 millimeter and Vs is 30 meter per second. So it is 1 into 10 to the power minus 3, sorry 3 into 10 to the power minus 3 divided by 30. So it is 10 to the power minus 4. So it is around 100 microsecond. So time required by the grit moves through the grinding zone with very less time of exposure, and because of that heat cannot enter the grit so readily. So this is first requirement, this is the first reason, and this is the second reason. Second reason is that as because it is moving through the grit very rapidly, heat doesn't get enough chance to enter it. So because of these two reasons, thermal conductivity of alumina grit in vitrified wheel being very low, because vitrified bond is also a kind of ceramic bond. Because of that reason, and grit moving through the grinding zone very fast, combination of these two reasons can lead to a situation where QS is 0. Now you might say, then what about QW? Then why QW is not 0? Please try to understand, if this is your heat zone, grit is moving very fast, but workpiece is moving at a rate of VW. How much is VW? VW is 6 meter per minute, that is 0.1 meter per second. So you can definitely not compare 0.1 meter per second with 30 meter per second. There is a order difference of 100. Okay, so because of that reason, heat does get a chance to enter the workpiece. Second of all, most of the time we grind metallic alloys, and the thermal conductivity of metallic alloy is very high. So that boils down our equation, which was written here, to QW plus QCH equal to QT. And this would be a very useful equation to estimate grinding temperature. And we are going gradually towards estimation of grinding temperature in dry grinding. Not only that, we are doing it only for conventional vitrified wheel. Once we go for super abrasive wheel, things will change dramatically. So at this stage, I will introduce one more slide and talk about something else which is not there. So this was 7th slide. So let me get this slide. This one here. What are the different grinding situations that can occur? So what is the most generalized grinding situation? Most generalized grinding situation is grinding with a super abrasive wheel using grinding fluid. In that particular case, my equation neither this term nor this particular term would become 0. Both of them would stay. Currently, QS is 0. Why it is 0? Because we are using conventional alumina or silicon carbide wheel. QW is 0. Why? So not QW, QFL is 0. Why QFL is 0? Because it is a case of dry grinding. So gradually we will introduce these terms. In the next subsection itself, we will try to introduce what happens when you employ a super abrasive wheel. That means without grinding fluid, but with a super abrasive wheel. And the final one would be with fluid. The final one would be equally applicable for grinding with a conventional wheel with application of grinding fluid. So once all the terms are taken into consideration, the most generalized cases can be solved. So we will stop here once again. We will stop our 7.1b and we will reassemble shortly.